Alright, let's do another one. Number 30 of the Grind 75 list, I believe. Yep, this is going to be number 30. Number of 1 bits. Oh gosh. Okay. Okay. Write a function that takes a signed integer and returns a number of 1 bits it has, also known as the Hamming weight. Note that in some languages, such as Java, there is no unsigned integer type. In the case, the input will always be given as a signed integer type. It should not affect your implementation, as the integer's internal binary representation is the same whether it is signed or unsigned. Okay. Example 3 represents signed integer -3. Let's see, that takes an unsigned integer. And returns the number of 1 bits it has. And I'm assuming that we are given essentially this number right here, probably with the ones truncated then. So basically we just need to figure out sort of how many times we can divide it. Oh gosh, this is gonna be another math heavy one. I can tell already that this is gonna be a math heavy one. Let's see. Input must be a binary string of length 32. So basically we're given that input. So the first thing I'm going to do is work in base 10. We're not going to be working in base 2 for the sake of the fact that I don't think there's any reason to complicate it and say like, oh, we're working in base 2 when all we need as an output is the number of zeros. So it really doesn't matter the actual value, whether it's signed or unsigned, whether it's base 2 or base 10. As long as our actual values, as long as what we are doing to those to the number is consistent. So in this case, let's see. Basically, we want to shift the value and check the last value if it's a 1 or 0, essentially, right? So we could do this recursively. Check if the last digit is 0. Then increment or not, and then divide by 10 and recursive call. So basically, if we'll say return, if n is 0, return 0. Otherwise, we will be returning if n mod 2, I think it's remainder. Actually, I think we can still do this. N mod 2 is 0 plus the Hamming weight of n divided by 10. So basically what this will do is that it'll check whether the last digit currently is a 1. And actually we can run this as an expression, I guess. So we'll do this. 1 else 0. I'm not even sure if this works, but basically if it's odd, then we return 1. Otherwise we return 0. And then this is the initial value. So basically if it's odd, then we add 1 to the number of ones bit. And then we also divide by 10 because it's base 10. Let's give this a shot and see if this works. Let's see. Let's print out the number. We start with 1011. And that prints out 11? Why is that? Why does this print out 11? Because division by 10 should not do that. I expected 1011, then 101. Let's see if this works. Maybe this if statement is doing some weird stuff. 11 and then 1. Why is this being weird? I want to see what this outputs. $128. 0, 1, 2. Yeah, 0. Sorry, 1, 2, 4, 8, 16, 32, 64. Is this base 2? This is base 2. And this is all unsigned. Is it all unsigned? What is the value of u then? -3. Okay. No, so it is signed. Okay. In that case, Let's start with you. So in that case, base 2 still has the same, it still has the same principle, right? I guess it just depends on sort of, not even sure if the parentheses around that works. It does, okay. I'm guessing all of these will work except for the negative one. Exactly, okay. So let's take a look at exclusively the negative one. So we start at -3. What is -3 mod 2? Is that -1? Let's go into the playground for this. Switch to 1.3 in case there's any discrepancy. -3 mod 2. Let's see if this... This really doesn't want to run. -1. Okay, cool. So in this case, let's import Kotlin math abs. I think that's the one we want. The problem then is that we also have -1. So I think we'll do a val num1s is equal to when n mod 2 is 1, then it's 1, n mod 2 is 0, 0, otherwise 30, let's see, because what I'm looking at, what I'm seeing when I'm looking at something like this and -3 is that we have a 2 here, we have a -3, then a -1, a -3, so this has all zeros or all ones except for 1. What if we did something like return the opposite? So return the number of 32 minus the output -1. Then the problem with that is that, how do I manage that? Or maybe we just take the absolute value of it. So what's positive? What's +3? +3 is 1, 1. If we take the positive value of it, and then we convert it back, Hmm. Then 32 minus Hamming weight of absolute value of n. I think this will actually be off by 1. Oop. No, Hamming weight. Because it was 32 and we want 31, right? Plus 1. But I'll have to do some testing for this. It's -3, then 3, then 1. What if we did something like 1, 2, 3, 4? Just do some random runs of this just to make sure that this consistently works. And it seems to do so. That's surprising that the pattern just holds like that, which I'm pretty happy about, honestly, that it does work. As the internal binary representation is the same whether it is signed or unsigned. Yes, but the way that it's treated, unless Kotlin has like a as binary sort of thing. As binary? To work with the binary representation of numbers, replace toInt and find. But I still don't really have too much information as to how this binary stuff actually works in Kotlin. I'm gonna give it a submission and let's see how slow it is in comparison to what we can do. So let's see. How slow is this? If we're having it each time, then this will work in what, log base 2 of n? Which I think is fine. If this function is called many times, how would you optimize it? We could probably do a lookup table as a way of sort of quickly giving the output as to some of the smaller numbers or some of the more common numbers. We could work with a lookup table. That's one way to speed it up if it's called many times within our program. What else could we do? Because at that point, we'd be basically just trading space for time. Because there's the only step underneath log is basically constant, and constant would mean basically a lookup as far as I understand it. So this let's work in base 10 was basically a lie. Ooh. We did an overflow. Oh, what if we did an absolute minus 1. Oh, but if I did, yeah, because this is right at 2 to the 32, right? Because 2 is complement notation, we can go 2 to the negative 32. Um, but we can only go up to 2 to the, or sorry, to 2 to the negative 2 to the 32, or to the 31, all the way up to, no, it's negative 32. Um, all the way up to positive 2 to the 31 minus 1, I think. It's been a bit since I've done some binary 2's complement stuff. Um, but yeah, this looks like an overflow. A very, very slight overflow. Um, the problem is that if we do something like, let's go back to negative 3, right? If we do this, it'll be 32 minus Hamming weight of absolute, that minus 1. In that case, we'll have 2, and that's 0. So that won't quite work unless we do 31 here. But then I'm not sure if that'll work for all the cases. Absolute n minus 1. Oh, no. Okay. Oh, but do we want to do the n minus 1 inside or outside? Because if I did it in the inside, then this would still overflow, right? Because this would go into positive this number minus 1, which would... This would overflow on its own, actually. So I actually do probably want to keep this, but then do an n minus 1 outside. Negative 3, then that goes to 2, then that goes to 1. So that actually is fine to keep it as 32. This is obviously not a very programmatic or a very thoughtful way of doing things. But hey, if it works, it works. Let's toss in a couple of random sort of numbers to mess around with just to make sure that this isn't just something that works for one number. And then we'll test it out on the extremes. Alright, cool. So that seems to work. Let's toss in the overflow number. So this should turn into int max, basically, and then overflow right back in. Oh, no, it doesn't. So this still refuses to work. Why is that? Fine. I'm guessing it's because it's overflowing as soon as we call the absolute values. So I guess we'll just have to do n plus 1 absolute in there instead. Why does that still not work? I'm pretty sure that's just 2 to the negative, or negative 2 to the 32, right? Or negative 2 to the 31. Yeah, it's negative 2 to the 31. Then 2 to the 31 minus 1 should be that, but for some reason that's not available. Are we actually getting a solid number when we do this mod 2? No way. How is that giving me a solid number? There's no way that this gives me a solid number. Unless this gives me straight up int max? No, but this shouldn't. What does this give? This gives me 0? Why does that give me 0? That is such a weird case. Oh, is it because it's a negative even number? Okay. Um, what if we do this then? What if we just do this? Oh, else, I guess return 0. I'm not too sure. Printing n is still pretty helpful, so we'll keep it there for now. So we'll move the n less than 0 to the top, so that this is the first case that it encounters. Oh, we do still need that case. So that we don't accidentally just return this indefinitely. Okay, so that actually works now. We go back to, basically we're just flipping this, we're taking the 2's complement of it basically. And then we're returning the 32 minus because that's the 2's complement way of doing things. Now that actually makes a lot more sense now that I'm like going over it in my head and be like, yeah, that actually does make sense the way that we're approaching it. I'm gonna toss in a couple more negative numbers just to make sure that that this still works, but should work. 2's complement sort of. Let's remove the 0 so we can test out another negative even number, just to make sure it works. Let's give it a shot. Okay, that is so low. Okay, that is like very, very, very slow. Surprisingly slow. Is there a way that I could do this faster? I mean, maybe you can just turn it into a string and just count them. Is there like a 2 binary string? I'm gonna take a quick browse through the Googles and see what comes up, and I'll be back. Alright, so apparently 2 binary string is a thing. So maybe this is what we want. So this returns a string, right? So we can do val binary string is equal to integer to binary string n, and then we can say var num1s, and then binary string for each character is 1 num1s plus plus, and then just return num1s. Let's just run through some example test cases. That also seems to work fine. For both positive and negative numbers. Let's toss in the edge case. Let's toss in the edge case one. That also does seem to work fine. As internal binary representation is the same. I mean, if that's the case, like we can do this as well. Like we just turn it, keep it as a binary string, the number, because internal representation is the same as they said. And in this case, we're just using a string iteration as well. Let's see if this is actually any faster. I'm not sure. We'll see if it is any faster. Okay, apparently it is. And probably a decent amount faster too. Yeah. I mean, I guess that works. I guess maybe sometimes the mathematical approach is just not the most efficient approach, and maybe there's just a way to use standard library functions and string manipulation to operate on it faster. I'm guessing the recursive calls also really didn't help. Um, Honestly, I'm I'm fine with this. How could we improve this further? I guess if we're working with this sort of method. I mean, in this case, we technically. I'm tempted to say that it's constant runtime because of the fact that there's no way that we can represent an unsigned integer value with more than 32 bits of. So at most we will have 32 characters to look at, no matter the size of the integer, as long as we're dealing with integers, right? So this is technically, I guess, constant time. It's a little bit weird, but I mean, I guess it makes sense to a certain extent. And then space, I mean, space, we're just keeping an integer value. Though I guess we're also keeping the binary string, but again, the binary string can only be so large, so I'm tempted to say that everything is constant, which is weird because I don't know, saying that both runtime and space is constant is like, something ain't right, chief. Maybe there's something wrong with my judgment here, but as far as I feel, like this is, I think, fine. My initial approach, I think, is also all right with the way that it works. Of course, it's a little bit slower because it does need to go through all those recursive calls, but I think this one makes more sense if we're sticking purely to the world of math. And then this one is sort of, I guess, the programmer's approach to it. But I think this is where I'm going to leave this problem for now, unless something else comes up. But in any case, I hope you enjoyed, I hope you learned something, and I'll see you for the next problem.